Hello, welcome to CE 3305. The topic of this lesson is flow in conduits. So a conduit is a pipe, tube, duct, completely filled with flowing fluid. The fluid could be gas or liquid. We're mostly going to use water in this discussion, but bear in mind that if it's gas and compressible, most of what we discuss applies, with the exception that density is no longer constant. The walls of the conduit bound the flow. If the walls completely define the flow tube, then the conduit is called a closed conduit or closed conduit flow or pressurized flow. If the conduit is only partially full, that's called an open conduit, and that's the subject of a different chapter. So examples of conduits are our friend the pipe, or perhaps a confined aquifer. In either case, the water is contained completely in the conduit. The confined aquifer, the walls are geological materials. And every house has to have a tree, because that's how I like to draw them. Okay, there we go. Things that are not conduits would be a partially full pipe. So, using our book, we could still have a pipe. We can have a different house. This time we'll use a shed roof. Everything's got to have a green tree. And instead of being completely full, there is a free surface. And in the case of aquifer, there is a free surface. So this is called a unconfined aquifer. So partially full pipe, unconfined aquifer, not a conduit. Full pipe, confined aquifer, conduit. So these flows in these pipes are classified as laminar tubular transition, and it's based largely on observations initiated by Osborne Reynolds of the Reynolds Aluminum Corporation. No, I just made that up. He was a physicist in England, I think, or in the UK. And he made these experiments using a device not unlike what I've sketched here. And he would introduce a dye into the liquid flowing through this long, slender tube. And he found out that if he limited the outflow so that there was one particular flow rate, that he could have a thread of dye, and it's long-lived. It endures a long distance in the system, and that was called laminar flow. There's some nice YouTube videos. I believe I have cross-referenced in one of the online deals. Found out if you open this valve a little bit more, so the flow rate increases. So we still have this constant head system. That now the dye stays together for a little bit, and then it starts to break up. but more or less definable. So he would have streaks of dye with some eddies. This has become known as transition. And then the last type of flow, when you just open the valve all the way and let her rip, so to speak. The dye would go there and it would break up and basically get completely mixed in a very short distance. So almost complete mixing. No strands remaining, no threads. And this has since become known as turbulent flow. There's no apostrophe there. I believe it would be that way. I think Reynolds, his name had the S in it. I could be wrong. Other than being grammatically correct, it doesn't matter a whole lot. So these were Reynolds' experiment. And he further discovered that the ability to predict this behavior, or the onset of surface of turbulence, was predictable based on the dimensionless group rho v d over mu. So there's this pi group, and that was able to predict onset of turbulence. And what that means in like practical terms is, depending on the value of this pi group, the analyst could determine if the flow would be laminar, transition, or turbulent. Now, beyond that, it didn't help much, but this was a valuable finding, and this pi group has since been known as Reynolds number. Usual symbol is Re. Put a subscript D to indicate that's a Reynolds number based on diameter. Rho v d over mu, and sometimes it's v d over nu, where one of these is kinematic viscosity and the other one is dynamic viscosity, absolute viscosity. One of the viscosities takes care of the density. I'd actually have to look that up in the book. I know a way to do it. Let's just go ahead and look it up for water, because I have dynamic viscosity and kinematic. Excellent. That's what I was after. All right, so there's our two ways of Reynolds number. This subscript changes depending on the characteristic lengths that's used. So for example, there's Reynolds numbers based on grain sizes, there's Reynolds numbers based on distance from a leading edge in a plate, and so forth. Whatever the variable is, it's going to have units of a length. It's going to be some kind of length. And so good name as any is the characteristic length. Okay, for pipes, turns out if the Reynolds number is less than 2,000, we have laminar flow. If the Reynolds number is bigger than 2,000 and less than about 3,000, and this will vary from book to book, transition. And when the Reynolds number is bigger than 3,000, we have laminar. Excuse me, we have turbulent. There's a property called, this occurs when the flow is fully developed, and so you have fully developed flow. when the velocity distribution in the pipe is a constant shape. Typically that takes about 50 diameters. So if we were to look back at our Reynolds experiment, the distance we would start looking at things, this would be about 50 diameters. And that matters in the experimental design. Most real piping systems, you can comfortably treat them as if they're fully developed flow. The textbook has a nice description of fully developed flow on pages 361 and 362 if you want to read more. So, what are the implications of fully developed flow? Imagine if we had a rectangular duct and it was 8 feet wide, 4 feet tall. We computed its area would be 32 square feet. It's this area here. Flow is coming at us, trying to poke us out in the eyeball. The wetted perimeter would be 8 and 8 is 16. And another 8, no, 4 and 4 is 8. So 24 feet. That would produce a hydraulic radius, term we haven't learned yet, but it's area over wetted perimeter. Would be 32 over 24. So 8 times 3 is 24. 8 times 4, that's going to be 4 over 3. So about 1.33 feet. And we would expect fully developed flow to take almost 50 feet in this configuration to occur. So if X is measured from back here, we'd have to go 50 feet to any kind of experimental conditions that we're interested in. So up here, we don't know what's going on, and from here on, it's fully developed. And if you imagine, if you actually think about those sizes, an experimental configuration of any kind of system, there's a fair amount of real estate that's used up before you get to the fully developed flow. Some of you will get to see experimental open channel flow configurations. In fact, you'll use them in your laboratory next semester when you take it. Bear in mind that the laboratory ones you use, it's very difficult to achieve true fully developed flow in the physical distances you have to work with. Okay, so that's just nice background info. Okay, pipe sizes. There's commercial sizes on page 363. And the sizing depends on the materials, pressure rating, and the ability to carry outside loads. So imagine what we do to a pipe as perfectly good engineers so that people don't trip over them or hit them with their cars. We tend to put them underground, although when we take the field trip to Berlin, you'll see pipes up in the air. So this is my pipe. And when we buy it and do the fluid mechanics part of it, we're interested in what the inside diameter is. But pipes also have an outside diameter. When we put them in the ground, we generally put them on some kind of bedding. There's my bedding material. Then we fill them with a slightly different material called the haunching material. Then we might use an initial backfill. You get my material, a little bit of green stuff in there too. And then finally we just do the final backfill, which is all the floor sweepings we can find. Okay, I'm oversimplifying and exaggerating that. In the US, the spring line is the center line of the pipe. This material below the spring line is called the haunching. I have no idea where that word came from. And then the pipe is laid on bedding. Initial backfill. Final backfill. And it's not too hard to see from this diagram that the pipe, in addition to carrying water on its inside, has to be able to resist these loads from the backfill and the surrounding material. And these can sometimes be quite deep. 100 feet, 30, 40 meters below grade is not unheard of. That'd be a very deep pipe. And so this soil overburden is a substantial amount of weight on top of the pipe, and the pipe has to be able to resist that load from the outside trying to crush it, resist the pressure load of the liquid on the inside trying to get its way out of there, and do it all for a reasonable cost. So point is, in our pipeline designs, in a practical sense, we also have to worry about the structural aspect, which is not part of our book. Okay, in pipes we use, oftentimes we'll find that Bernoulli's equation can be used with the addition of a head loss model, and that was called the modified Bernoulli equation. So imagine some pipe going from location 1 to location 2. I've intentionally drawn it as going uphill, so we'll assume that I'm going to specify that that is the flow direction. We have some horizontal datum here. And as per Bernoulli's, we would call that Z1, that Z2. So those are the elevations with respect to the datum of the 2 points in the pipeline. Then the pipe would have some internal pressure, P1 over gamma P2 over gamma. And lastly, if it's Bernoulli's equation, there's no energy loss, so there would be V1 squared over 2G, V2 squared over 2G would be the velocity head. So we have the three head turns. Okay, so in Bernoulli's we would write P1 over gamma plus Z1 plus V1 squared over 2G equals P2 over gamma plus V2 plus Z2 squared over 2G plus Z2. There's no losses. Now, that's not realistic. So real pipelines, instead, there are observed head losses. So let's redraw the picture in a little bit more realistic fashion. There's my point 2, there's my point 1. And because of head losses, that energy line, which we think is flat, actually slopes downhill in the distance towards the pipe. And try to get my pressures more realistic too. So this is P1 over gamma. Here's P2 over gamma. V1 squared over 2G, V2 squared over 2G, Z1, Z2, and we're now interested in that distance, which is the head loss. If we incorporate that, our modified Bernoulli's equation becomes P1 over gamma plus Z1 plus V1 squared over 2G equals P2 over gamma plus Z2 plus V2 squared over 2G plus that head loss. And we represent those head losses using head loss models. Okay, so Marie Antoinette was a classic head loss model, but without regard to the French Revolution, we have some other head loss models to look at. Okay, so the head loss models, that head loss is total loss. It's not like there's like a little string of connective tissue keeping the head still attached to the body. And those total losses are comprised of pipe friction, which is also called the pipe loss component, junction, friction, frictional losses induced by bends, transitions, inlet, outlet. These ones grouped collectively are called minor or fitting losses. And don't let the word minor confuse you as to the magnitude. They're called minor because they occur over short distances, whereas pipe friction occurs over long distances. Fitting losses is probably a better generic term. These tend to be somewhat empirical, but over many years of engineering, they're made to look like a pipe friction model. All right, so the common pipe friction models are Darcy-Weisbach, Chesney-Manning, and Hayes-Williams. I believe our textbook uses Darcy-Weisbach almost exclusively. Chesney-Manning is not common for pipes. And Hayes-Williams is for water only. And I'm pretty sure it's specific to the United States. The next step after this video will be to go through a plausibility derivation, I guess that's the best terminology, to illustrate where the Darcy-Weisbach head loss model comes from.